Hello, welcome to another tutorial. In this video, I present a simple example using the FPGA on the ANT board. For the UART module, I use a core IP provided by the manufacturer. An IP is like a library that handles everything needed to perform a specific function. The IP core must be added in the project panel in the subsection called IP. I've already added the IP, but to add this module, you right-click on IP and choose the option New IP. Then we wait for the IP catalog to open. Please note that if you want to learn how to create a project from scratch, I suggest watching the video titled Turning on a LED with a Push Button on Efinix Trion T8 FPGA, which I've linked in the description. In the catalog, open the installed IPs. In the Efinix section, I look under Serial Interface Protocols for the UART option and click the Next button. A window opens showing a graphical block of the UART. I selected 1 byte to transmit. I left the clock frequency at the default value of 50 MHz. The baud rate is set to 115,200. I enabled fixed baud rate. Since I don't use parity, it doesn't matter if the checkbox is set to odd or even. I also don't use the bootup option. In the graphical view of the module, you can see the input terminals: receive, clock, reset, baud rate, transmit enable, and the byte to transmit. The output terminals are the transmit pin, the TX busy signal, the received byte, the RX error flags, parity error, RX busy, and enable tick from baud generator. On the tab called Deliverables, we can select to generate an example, in this case for 2 types of FPGA and a test bench for an IP simulation. We also have a tab that gives us a summary of what has been configured. And before generating the IP, a name must be given to it. In my module, which I have named my UART, I have the following parameters. The inputs are CLK, which is the clock signal, PLL inst1 locked, which I will explain later what it's used for, and RXI, which is the receive terminal. The outputs are TXO, which is the transmit terminal, LED, which is the pin that controls the LED diode, and another output called PLL inst1 RSTN, which I will also explain later. Before I continue explaining my module, I need to show how I configured the FPGA terminals. So I open the Interface Designer. Here I have a frequency multiplier, also known as a PLL, which will allow us to get the 50 MHz needed for the UART from the 33 MHz of the board's crystal. We can open another window to calibrate the PLL, and we can see how it's been configured to reach the required frequency. I have 2 pins that I could disable, but I prefer to use them. The first one is the reset pin, which I mentioned earlier, and in my module it's used as an output. The other one, which I also use in my module, tells me when the PLL is locked, that is, when it has reached the desired output frequency. I close this window and move on to the GPIOs. The terminal I want to point out is the one called PLL inst1 CLKIN, which is a logic input, but it's also a PLL clock input. And obviously, here is where you put the name. Then, the LED diode terminal is the same one used in the last 2 videos, which I've linked in the description. The receive terminal corresponds to pin A8, which is configured as an input. I enabled a pull-up resistor to keep the line idle in case the transmission from the other side gets disconnected. And the transmit pin is an output and corresponds to terminal B8. I can open the resource assigner to view the terminal assignments of the FPGA. In this image, you can see the board terminals that will be used for transmission and reception. There's nothing special about them, they could have been any of the available ones on the board. Back to the code of the module in my project, the first thing I define is the internal terminals that will be used by the IP described earlier. Then I have a 2-bit array for the baud rate, and when the value is 0, a speed of 115200 is selected. Next, I have the transmission data bus, its enable bit, and reset bit, which can be initially set to logic 1. Next, I set the frequency multiplier terminal to a logical 1 so that it operates normally. Maybe it wasn't necessary to enable the use of that terminal. Then, I have a 2-bit vector type variable because I am going to create a state machine for the UART operation. There are 4 states, which will be explained in more detail later. For now, it's important to understand from the user guide of this module that the data must be sent within the duration of 1 baud rate pulse or tick, and therefore, the TXN bit must be held at a logical 1 for at least that period of time. One solution would be to use some timing method to measure a pulse of the baud rate. The other option I used was to analyze the bit that indicates whether the transmission is busy, using this diagram. In this diagram, the clock signal should not be confused with the 50 MHz oscillation frequency. It refers to the UART baud rate clock. In my case, to ensure that TXN stays at a logical 1 for an appropriate amount of time, I follow these steps. 1. Set TXN to logical 1. 2. Wait for TX busy to change to 1. 3. Once TX busy is at 1, wait for it to return to logical 0. 4. Finally, I set TXN to logical 0. This way, I ensure that TXN stays active long enough for the transmission to work, and the UART will be ready to transmit another byte when it is no longer busy. Here, I create an instance of the IP module, and assign all the terminals it needs to operate correctly. Here is the always loop, which runs on a 0 to 1 transition. The first thing that is checked, with the first if statement, is that the frequency multiplier has stabilized. As long as that condition is not met, meaning inside the else statement, we can use it to initialize anything that needs to be set up before the main process runs. In my case, even though reset is already at 1, I set it again, turn off the LED, disable the transmission, and start the state machine in its first state. Then, if the PLL has stabilized, another if statement is executed, where it checks if reset is 0. But since it is 1, the else statement is executed, where it is changed to logical 0. This way, it ensures that the UART module has been in reset for at least 1 clock cycle. With the UART reset set to 0, the first state of the state machine is executed. It doesn't really make sense because it sets reset to 0 again, but I kept it that way. The next state is important because here I wait for a byte to arrive from the host to the FPGA, and also, for safety, I check that the transmission is not busy. If a byte arrives and its content is equal to 5, I turn on the LED diode. If it is equal to 7, I turn off the LED diode. I increment the received byte by 1, place it into the transmission array, and then enable the transmission. In the next state, I wait for TX busy to change to 1, and when it does, I move to the next state. In the final state of the task, I now wait for TX busy to return to 0. If that happens, I disable the transmission and go back to the state where another byte is expected to arrive from the host. So, it looks like I'm ready to run a test with the hardware, and I hope it works. Here is the Antfire on a protoboard, and you can see that it has the project from the previous video, which I've linked in the description. On the right, there is a USB to UART converter, and the transmit and receive lines of both modules are connected through 330 ohm resistors, which I added for safety to prevent a short circuit between them in case of a possible misconfiguration or connection mistake. I ran the project's synthesis and I'm waiting for it to finish. I sped up the video so we don't waste time waiting for the completion. Once the project's synthesis is complete, I open the programmer, load the hexadecimal file, and flash it into the Antfire's memory. I close the programmer, and here I have a software that lets me send information over a COM port on my PC called Hercules. I will open the COM port and send a byte equal to 1. You can see that it returns the number 2. Now I send the number 5, and the LED diode turns on. Also, the FPGA returns the number 6. To turn off the LED diode, I send the number 7, and it worked. The LED diode turns off, and the FPGA returns 8. I send the number 9, and it returns 10, or A in hexadecimal. And finally, I turn the LED diode back on by sending 5. That's all. Thanks for watching the video.